Welcome, everyone. Today, we're going to be talking about how to approach erasing personal data in a distributed system, and in doing so, pay your users a little respect. My name is Neville Samuel, and I lead the engineering team at Ethica. We're a tech startup that helps businesses automate data subject rights for their applications, like access and erasure requests. Overall, though, our vision is to be the trust infrastructure of the internet. To do this, we're building tools to help engineers create more respectful systems. And this applies to all stages of the software development lifecycle, starting with better developer tools to design and annotate data while it's being developed, all the way through to production, where our hosted platform can integrate with your applications to improve personal data rights. After all, deleting someone's data when they ask you to is hardly a big request. It's simply providing users with a little respect. Today, we'll start by reviewing some of the key concepts related to erasure, and then focus on a simple example of erasing data in an application database and traversing a tree of related entities. We'll then discuss how to connect this across multiple data stores, and then wrap up with some advice on designing respectful systems. For today's talk, we'll use a simple example of an e-commerce application. Let's assume we have a couple of front ends that collect data through a store and a checkout app, probably some kind of order service for inventory management. These all connect to a shared Postgres database that acts as our primary data store, as well as a Redis session store and a Snowflake data warehouse for analytics. Looking at this application, you should be able to guess what kinds of personal data might be stored and where. Some obvious examples would be tables for users and delivery addresses, but there will also be related personal data in tables like orders and favorites, although not identifiable alone, still belonging to the user and therefore should be erased. Also, that warehouse is going to store lots of analytics, events, and historical records and things like that, all of which are going to be chock full of identifiable information. So let's remind ourselves what erasure is really about. The right to forget. This is a fundamental feature of a respectful system and is included in most privacy regulations. The one most people are familiar with is the GDPR Article 17, which gives data subjects the right to request that you erase all of their personal data from your systems. GDPR allows 30 days to do this, while CCPA has a similar provision that allows 45. And this is why so many businesses actually do this manually because, frankly, the timescales are quite large. Overall, though, there are a lot of restrictions and exceptions to these rules, but that's really not the topic of today's talk, so we'll just leave it there. Now, on the surface, erasing a user's data sounds pretty simple, right? You just need to delete their row from the user's table. Now, in practice, though, this is probably not going to work for a variety of reasons. First of all, personal data is never just in a single table, right? It gets copied around and spread across all your different systems. So if you do delete that user record, that can end up leaving these orphaned records behind without any way to associate them together, effectively breaking the referential integrity of your database. Now, also, if you delete entire rows like this, you'll often be removing non-personal data as well that was related and stored together. And while you'll note that in theory, you could do a cascade delete in a single database, there's not really an equivalent for this to cascade across multiple interconnected systems, like our connected warehouse, for example. So because of all this, personal data erasure tends to be an application level concern that requires a lot of custom engineering. Now, while erasure requires us to forget all the personal data about a subject, it doesn't mean that you need to necessarily be deleting those entire rows from your database. In fact, given that this will also remove anonymous data and like aggregate row counts and usage information, most of the time businesses probably want to selectively erase the individual fields that contain personal data and erase those in order to preserve that aggregate information and avoid those integrity issues we talked about. So in other words, if you can, prefer deleting those rows because it's the simplest. But today we'll focus more on using updates to selectively erase fields instead. Now, the basic algorithm for erasure is simple. You receive a request from the user, and from that, you get some kind of identifying information like an email address. Then you use that identity to collect all the matching row IDs from your system, and then from there, branch out to collect related row IDs and other related IDs, and kind of repeat this process to form somewhat of a tree of interconnected rows. Then you can iterate across all those different rows and erase personal data along the way. So let's assume a really simple user table to highlight this that has just an ID, an email, and a name. We'll use sudo Python for the example code in this talk. And here's kind of like the overall entry point to just deleting that user row. There's nothing surprising here, really. You just kind of bring in the email address, use it to query the matching user IDs based on that email, and then loop through each to erase the personal data associated. Now, the implementation of that row-wise erasure for a user can be either an update or a delete, as we discussed. So as you can see here, the update is a bit more complicated, as we need to compute new user values for that row. In this case, we're just simply assuming we have some helper method that we'll take a look at it called compute hashed user values that does the real work here. And then our function just runs an update statement to erase those fields. Here's an example of implementing hashing as a strategy to erase personal data fields. Now, using a one-way hash like this, instead of simply nulling out a field, can be very helpful if done in a secure way because it anonymizes the data. Now, everyone thinks hashing is trivial, but it's not. So please use a real library to do this, and always remember to provide a salt. In fact, if you use a consistent yet random salt for the entire erasure request, you can consistently anonymize something like the email address to the same hash across different tables, which can be very helpful. And it might be actually necessary for your application to do this. Lastly, just notice how we're having to write custom code for this user row instead of relying on some kind of generic database routine, right? This is highlighting that erasure strategies need to vary depending on the underlying data types, like strings or numbers or timestamps. And it also has to vary based on the category types. Like you may need to treat emails and names differently from something like an address information or whatever other kind of constraints your application may provide, like uniqueness, etc. So once that erasure step runs, we're left with an anonymized email and a name, but you'll see we've intentionally preserved the row and the ID. We'll use that user ID to find related records in the next step. All right, so once you've seen the basic algorithm, the traversal across tables in the same database or distributed across many is effectively just repeating the same thing. So in this example, let's assume a user has many addresses and orders, all of which need to be erased. So for each user request, we then perform the same steps on those related tables to collect matching IDs and erase the data. So let's take a look at those now. Here's our address table that needs to be erased. So in this case, let's assume that maybe hashing isn't as important like it was with the email address, as this data isn't copied around and joined across the tables. So therefore it doesn't need to really maintain consistency. So we start with the same basic search to identify which rows need to be visited and collect those and loop through each. And then we run those update statements for each related address. But this time, let's assume it's okay to just set everything to null instead of kind of computing those hash values like I mentioned. And here's what that leaves us with. Now, you'll note that we're still choosing to preserve the user and address IDs here, right? Which therefore tells us that an anonymous user did exist who had two addresses. This type of preservation of anonymous data is probably okay, but only if it's truly anonymous, and you'll have to be the judge of that. Now, lastly, let's look at our orders table, which is an example where deleting the entire row might actually be impossible. This table stores a record of each purchase. So because of that, we need to remember to retain the state and transaction amount for tax purposes. So we can't erase it. At least not unless we're absolutely sure that we have that minimal data copied to some other auditable financial system. However, we can erase the order email address. And in this case, let's assume that we only need the aggregate number of orders, we no longer need to link those back to anonymous users. So we can go ahead and null out those IDs as well. So the code for this is pretty simple. We null out the email, but we choose to preserve the state and the transaction amount, like I mentioned. And then lastly, we go ahead and choose to null out the user and address IDs to unlink this record entirely. Again, this will still preserve the aggregate order count, but it'll remove our ability to accurately compute statistics like the number of users who entered at least one order. And here's the result of that operation. Pretty straightforward. Okay, so we've seen how we can erase 3 related tables across users, addresses, and orders. Now in practice, the traversal order here does actually matter. And I'd recommend you start by crawling all the relationships to build out a tree like this, and then erase them in reverse order by starting from the leaf nodes and working backwards down to the root. The reason for this is simple. If you do this and along the way you choose to unlink records or delete rows, going in reverse order maintains the integrity of the system throughout. So even if the erasure gets interrupted midway through, you could resume it and finish it afterwards. So here's the combined pseudocode that leverages those 3 row-wise helper functions that we wrote along the way. Overall, we start by collecting all the user IDs, address IDs, and order IDs that we'll need to visit. We then erase them all in reverse order and return the total number of rows affected by the operation. So, now that we've demonstrated the basic algorithm in our primary database, let's move on to the warehouse and the session store and talk about some special cases there. Data warehouses are basically the same thing that we just did, but they do have some key differences. Warehouses tend to have long chains of related tables, many of which are often denormalized, which makes them easier to ingest in analytics software and visualizations. So because of this, you'll often be left with lots of copies of personal data instead of just tables that are linked by foreign keys. Furthermore, they often don't have the same kinds of indexes, especially not on the things that your eraser algorithms want to index on, like email addresses or user IDs, and instead they get partitioned by things like date. This means that overall, erasing personal data from warehouses is just slower than in application databases. So my advice to all of you is this. The best way to erase personal data from a warehouse is to just avoid storing it in the first place. Trust me, you can get an enormous amount of business value simply using anonymous IDs in your analytics warehouses and save yourself a lot of trouble. However, let's assume we didn't do that, and we've decided to store personal data in something like an events table in the warehouse. It might look something like this, where you have that user data copied into thousands of these events, all of which are intertwined with events from other users. So our basic algorithm will still work, of course, but it will require visiting thousands of these rows and not in a particularly efficient way. So we're not going to dwell on this too much here. But the basic problem is that these row-wise updates tend to just be slow on analytics schemas. So 2 strategies that might help is to think about doing bulk updates instead. So for example, you could compute that anonymized user data once and then bulk apply that to all the matching rows in a single statement. Or another option might be to look at how your schema is actually partitioned and then run bulk updates for many users at the same time for the same partition. All right, so we're starting to run short on time, so let's leave our exploration of warehouses there and assume we've covered things and make one more stop over in our Redis store. Unlike Postgres, Redis is a key value store, so everything we've discussed about rows and tables is a little bit different. Now, the algorithm, though, is essentially the same. You take that user ID, you find the related documents, and then you traverse your Redis structure based on however you designed it, and then run erasure on each of those records. Now, the syntax for doing all that is completely different, but the general principle still applies. However, maybe we can take an entirely different erasure strategy here. If we assume this Redis store is acting as a cache for session values, and we use expiry dates for every key, That means as long as that expiry time is fast enough, we can simply let this Redis cache erase itself. Again, as long as that happens within that 30-day window, we're fine. Now, 30 days is actually an incredibly long time to wait to expire a cache. So why not just do this every 60 minutes? This kind of thing is starting to demonstrate what I mean by respectful systems. If you go ahead and take a proactive approach to data privacy from the start, you can dramatically reduce the complexity of erasure later on. So a few questions to ask yourself in the design phase include things like, how much user data is really needed to be persisted? Could you, for example, temporarily collect the user's address for shipping purposes and then forget it as soon as that order is placed? So since our example application, let's assume, was designed to expire any user data in that cache every 60 minutes, we don't even have to touch Redis. So therefore, our erasure is complete. Okay, so at this point, it's worth stating the obvious. This is not a very realistic example. Most real-world applications aren't going to have 3 tables. You're going to have hundreds or thousands of these data sets, each of which you'll need to sit down and write some kind of custom erasure function to implement this algorithm. At Ethica, we build tools that kind of help make some of that easier, but really there's no free lunch here. Furthermore, we've also only discussed well-behaved structured data sets. Personal data that exists in blob or file storage can be way harder to effectively query and erase in the same way. But why is that? Compared to a lot of the things we build in the tech industry, why is it so laborious to erase a user's data when they ask you to? In many ways, I think it's because we're not designing systems respectfully. We're designing them for convenience. So for example, think about a database. It's very convenient to go ahead and capture a bunch of personal data you might not need, store it in string fields. Those will be compressed and optimized on your behalf, and then you can copy those around as much as you want without even really considering it. But the respectful way to do all of this is actually to capture minimal data in the first place, keep it in one secure location, and then painstakingly maintain detailed metadata about what categories of data you've collected, why you needed to collect them, and where you save those. Now, databases don't do any of that for us, so it's actually a big inconvenience to design systems in that way. But we believe it's the right thing to do. So in summary, to provide users with a little respect, you're going to need to erase personal data across your systems. Start by building out that connected map of databases and where the personal data is stored. Then query the primary store to start collecting IDs and build that relationship tree across all the related systems. Traverse the tree in reverse order and delete personal data from each row, preserving anonymous data along the way where necessary for things like financial records. Now, for data warehouses, you'll likely need to use bulk updates to do this in a performant manner. And lastly, remember that the easiest way to erase personal data is simply to not store it in the first place. Or if you do, automatically expire it on some short time scale like hours, and then you'll be well on your way to designing respectful systems.